Okay, so we have the nebula collapsing to form stars. And as it collapses, Kelvin-Helmholtz contraction, governs the gradual collapse of the star, okay, of the protostar. When the protostar finally squeezes to the point that it starts nuclear fusion, becomes a star. So we've covered all that in the last couple lectures here. Starts in the upper right of the HR diagram. If it's really massive, goes straight over to the main sequence. Really low mass, goes straight down to the main sequence. Mid mass kind of drops, jiggles over, and falls down. Starts right along the 0 age main sequence. So that's the starting point on the HR diagram. Over time, it will gradually move off of that spot, but not very far. So it's still in the same general area. And that's why so many stars in the sky, tend to line up right along the main sequence. How big can a star be? We realize that stars that are really big are going to be so bright, they're going to be pushing their outer layers off in space. Remember the Eddington limit. The Eddington limit is the brightest that something can be before the Eddington limit here is the brightest that something can be before the sunlight actually pushes it. I mean, the light of itself pushes everything away. And so there are stars out here that are close to the Eddington limit, mass-loss stars, that are losing mass into space. Theoretically, it goes with the mathematics, about 200 solar masses is about as big as you can be before the Eddington limit pushes everything away. Now, in practice, we've not seen anything bigger than about 150 solar masses. So what does that mean? Theory says 200, practice 150. Now, I will admit, once in a while, I've seen something in the news where they say, brand new star, 250 solar masses discovers, challenges theories of astrophysics. And then they later figured out that 250 solar mass star is actually a cluster of about 5 stars. And so they're all quite smaller than this. Okay, but we have not found any single star really over 150. So that could mean two things. It could mean that there's something we're not accounting for that stops it at about 150. Maybe something with the interstellar medium with the nebula itself. Or it could be that stars bigger than 150 are so rare that only 2 or 3 form in the entire galaxy, and they don't live very long, and we haven't found them. So we're not really sure. Next question, what's the smallest star? I mean, you don't get nuclear fusion from just a blob of hydrogen gas. Jupiter is mostly hydrogen and helium, but it's not fusing. So where does this come from? Or rather, where's the smallest? What's the smallest possible star? Well, Joe Tarter comes up with this name called brown dwarf for these really tiny little stars. And so we calculate the smallest star that can initiate nuclear fusion is really close to 0.08 solar masses. So, okay, so something smaller than that forms just like a star. It's a protostar that never starts fusing, so it never turns into a star, and so we call it a brown dwarf. And I remember they were searching for brown dwarfs when I started graduate school. Very first conference I went to in astronomy, there was a session on brown dwarfs. All the researchers reporting their searches for brown dwarfs and not finding anything. And finally, though, the very first brown dwarf discovered was Gliese 229b. And it was discovered at Palomar Observatory This is Gliese 229 right here, which is a red dwarf. And that little dot right there is the star. The Hubble telescope is actually able to see the star. We do spectral analysis of it, and we find it's way too cool to be a star, but it's too hot to be a planet. So that makes it a brown dwarf. So today, we got a couple thousand of them we've found. The idea goes all the way back to the 70s. 90s, we first found them. Okay. And so, so now we got a couple thousand we found. They're really hard to find because they're so dim. Interesting enough, if you get a big brown dwarf, it's smaller. What? Okay. If you add more mass to a brown dwarf, then it has more gravity, which squeezes itself smaller. So a brown dwarf of 0.07 solar masses is actually a little bit smaller in size than a 0.05 solar mass brown dwarf. The most massive brown dwarfs actually squeeze themselves so much they fuse lithium a little bit of deuterium. Now, lithium turns out to be super easy to fuse. And so that's why Edward Teller, when they were building the first hydrogen bomb, they couldn't figure out how to make the hydrogen fuse like it does in the sun, so he thought about lithium hydride. And so the lithium would actually fuse with the hydrogen. Actually, he even cheated a little further than lithium tritiide. But that would fuse even easier. And so some of these things will fuse a little bit more easily than just plain hydrogen. But it's not enough of that to sustain it and to make it a star. So these massive brown dwarfs get close to being a star, but they still fail. In size, brown dwarfs, a little bit bigger than Jupiter, but way more mass. So your typical brown dwarf is going to be 50, 60, 70, or 80 solar mass, 80 times the mass of Jupiter. So 50, 60, and so forth. Jupiter, their planets go up to about 10, 20 times the size of Jupiter, but there's this gap between the biggest planet and the smallest brown dwarf. Okay. So again, brown dwarfs can get down, some of the most massive brown dwarfs can be really close to the size of Jupiter, but they can be 70 times the mass. Well, in recent years, they found a couple of these things that are between planet and brown dwarf size. So they're like, if a brown dwarf is a failed star, this is like a super failed star. And so sub-brown dwarfs, we don't even know what to call them. They're too big to be planets, too small to be brown dwarfs. We don't even have a name for them yet. This is when they introduced the spectral type Y to accommodate this basic idea. Well, interesting thing, if you've got this accretion disk, so you got a protostar, you have all this stuff coming in, you got an accretion disk. Well, the accretion disk has all the stuff in the interstellar medium in it. What's to stop the accretion disk from clumping up and making little small things orbiting around the star? What would you call such small things? Planets. So what happened was, American astronomer Otto Struve suggested that planets might actually form in the accretion disk surrounding protostars. Now, he did this before they'd even found accretion around protostars, before they even saw the protostar itself, because it's all hidden by the Cocoon Nebula. But he still worked through the mathematics of it and said maybe this happens. And so, in fact, if we look into the Orion Nebula, the Hubble telescope sees these young stars and protostars with these accretion disks around them. Now, once the protostar gets hot enough, it pushes away the accretion disk, it stops accreting, but that disk hangs around for a little bit, and it can quite possibly clump up to make planets. Now, what do you call such a leftover accretion disk that's clumping up to make planets? Well, you don't want to call it a accretion disk anymore because it's not accreting. What would make sense is you're making protoplanets, call it some kind of protoplanetary thing, except the term protoplanetary was already used to describe a nebula that's becoming a planetary nebula. So the term they came up with is a proplyid. A proplyid is this leftover accretion disk surrounding a star that is forming planets. And so we'll get to that coming up about planet formation.